Right. So next I was going to talk about this bio-inspiration once again. And so when we design such kind of rehabilitation robots, there's a lot of bio-inspiration. What do we mean by bio-inspiration is like understanding how our biological system works, and then trying to get into take that information to our robot designs. Just not design. In fact, we try to take that into robots design, how it should be actuated, how it should be controlled, how it should be inferred, what kind of information should be taken from the robots, and how the information should be analyzed. Everything has to be linked with a biological system. One of the aspects you've seen how the knee joint has to be always aligned with the robot joint, and that's one example of bio-inspiration in the design. So there are many others, and so yeah. So the biological system that we talk about have gone through a lot of evolution, right? And nature evolves things in a very optimized manner. There are certain features that needs maximization and improvements, and so it's a whole life cycle of evolution that goes into our robot designs as well. So when you're dealing with a robot for rehabilitation, one has to be very careful whether the robot has gone through such kind of evolutionary stages or not, and then only you can be confident of using it with the human user. So let's quickly take some interesting examples of bio-inspirations from and that's been utilized. For instance, this neurobiology. Okay, it plays a very crucial role, of course. And if you've heard about the rover, the Pathfinder, Mars Pathfinder. So the scientists, from NASA, they sent a robotic device to Mars to explore many things. There were inhibitions and anticipations that the surface on Mars is not going to be quite smooth and quite challenging. It's going to be quite challenging. And so the rover design, the Mars Pathfinder's design, has to be something that it can actually, it can easily move around and explore better. And so they used the design of this rover, the Pathfinder, was inspired from basically a 6-legged insect. And that was a very interesting example. So we normally try to understand the biological system and then incorporate in our designs those things. For instance, if I'm moving my limbs on a particular trajectory, I would like to find out what should be the trajectory of moving limb that would require minimum of the energy, or trying to optimize the efforts, right? And because that's how the human body has been evolved over the time. So, for instance, if I'm designing an exoskeleton, the exoskeleton is supposed to move my hand or legs. Now, to control it, to give it a trajectory to move on, how do I find this trajectory? So I have to go and check with the biological system how the human arm, hand, or the leg would move, and what is the most optimal way it should move, and then only I can give a command to my exoskeleton, and that will move the human leg or hands in turn. There have been many interesting applications, such as this parallax motion in insects. So this is not contextual, but still we can talk about it. The insects, especially if you talk about the flies, the most notorious flies, it has lived with humans, I think, since ages, and has troubled us a long time. the fly would sit on stationary objects. The moment you move it, it'll fly away, right? So how will it find something that is stationary? So it uses a parallax motion. So with eyes, the flies can detect relative velocity of objects moving. For instance, if you're traveling in a train, okay, so what you observe is that things which are closer to you move faster, and things which are farther from you move slower. Okay, this is something called parallax motion, and flies are very good at detecting it. So they know even before you move towards the fly, it would know something's moving and coming close to me, and would fly away. So such kind of parallax motion insect, it was kind of implemented in a special robotic mechanism, which is called robot. And so we do try to take inspiration from the nature, and then we try to improve our robots and our systems. So much so that we have even, developed algorithms that works on the basis of evolution. One of such algorithms is called genetic algorithm, if you've heard about it. Even deep learning and machine learning, they're all based on evolution that has gone through in human biological systems. So when I design a robot, for instance, I have to optimize many things. The robot weight should be very light. It should be able to give me required torques, and the mechanisms should be stable. Sometimes the mechanism could be very complicated, and it can, it can become fixed. So there are certain pointers that we need to optimize, and there we used, in my previous publications, also research, also we used a lot of genetic algorithm and deep learning kind of things, which are again, they're having inspiration from the biological system. So I just try to mention it here. And so it's a bidirectional move. We try to study the biological system and then design the robots. And once we have designed the robots, we use them with the subjects. And there are many sensors on the robot, right? Through sensors, we collect more information about the biological system. Okay, so the robots can also help us understanding the biological systems better. These sensors could be, as I told you before, could be biosensors, where we take signals from brain, signals from myographic signals from the skin. There's ENG. Different kinds of signals can be obtained from the human system, and then further working on these signals that we obtain from the robot gives us more information about the human system. One other thing is that while using, an exoskeleton for a patient, for a disabled person, and we're trying to, rehabilitate the person, what happens over the time is that the person's limb functions are improving. What we are trying to improve is range of motions and the strength. So we're trying to basically improve how much motion the person can achieve and how much strength is regained. So obviously over the time, we expect the person to improve. Now, how do we quantify that? How do we evaluate? How do we assess the person and person's improvements? It's pretty difficult. You need a lot of experiments to be conducted in biomechanics lab to evaluate person's strengths and motions. But with these kind of exoskeletons, while they are trying to rehabilitate person's lost functions and strengths and motions, at the same time they are evaluating, measuring those functions as well. How it is done, again, as I said, through these sensors. Simple displacement sensors can be used to see how much the person is able to move. and how much he's not able to move. And so what kind of settings do I need in my robots? For the strengths, of course, I can use 4 sensors. But if you remember, I was telling you that we want the person to be in charge of the robot. So what I was trying to say is that when the person is improving, we want the person to further work harder and harder and take help from the robot as minimum as possible. So that over the time, the robot's role should diminish, should decrease, and the person who is taking this therapy should be involved into the treatment more. Now this has to be done very smoothly, right? With the Locomed that we have, there are settings that you can manually change, and then you can decrease robot's torque and let the person apply more torque and so on. So, but the one which we are trying to work with can actually assess how much torque a person can apply, and then whatever is the deficit will be given by the robot. So for instance, if I'm lifting something, if I'm lifting my cup and bringing it here to drink, I need some, for instance, I need, let's say, some amount of torque, okay, X amount of torque. So the robot controller should be intelligent enough to find out how much torque the person can apply. And then if I need X amount of torque and I can only apply Y amount of torque, so X minus Y has to come from the robot. Now, to find that kind of thing, these sensors can help us, and then it's a bit complicated thing, but I can maybe explain it to you in such a way that, for instance, if I have to design a controller, okay, to move something, so I should know what I'm trying to move, okay, and what are the forces and accelerations and velocity, displacement, everything. And that's called modeling. So I need to model the system that I want to control first. I should know what my system is, and then only I'll be able to control. To know what my system is, it's very difficult when we talk about these rehabilitation robots, because in our rehabilitation robots, the system is human body. And to understand human body and to actually model it, it's quite difficult. It's almost impossible, because there's a lot of subjectivity. Everybody has different strengths and motions and ranges, and even physiologically, we all have different, sizes. Like my hands could be shorter than someone else's hands, and so these anthropometric measurements again vary from subject to subject, and so to come up with a model of a human body, it's not easy, isn't it? But still, we try, and we try to model, because otherwise I cannot design a controller and the robot cannot work. And so, I mean, there are many such kind of models available. There are softwares available which can create models of human body. You might have come across some of these softwares where you can actually model human body. If time permits, we'll also go through one or two such kind of softwares and try to understand how to model human body, how to evaluate the torques and motion trajectories of various limbs. Yeah, but here this HAL, it's a Japanese company, Honda. It's a Honda company. They have come up with such kind of a robot. It's like full body, both upper limb and the lower limb, and they use bioelectrical signals. So basically, they're using EMG signals to control this exoskeleton. So in their case, it's simply as if, when the person is trying to move, okay, the person is not capable of moving something, but he's trying to move his limbs. So there'll be very small activation that can be sensed through the muscles. If you can find that small activation in the muscles, you sense it, and you tell the controller that the person is actually trying to move, and then the controller would actuate, would start the motor or whatever the actuator is, and the robot would move. So, yeah, we were talking about the bioinspiration, and most of it is that it goes into many things. As I said, design, actuation, controller, appearance, many similar things. When you talk about appearance and actuation, for instance, see, if we have a human leg like this, okay, and if I'm trying to design a rehabilitation robot, okay, so I should try. I mean, previously there were different kinds of robots which would be quite intimidating and quite mechanical, quite industry type of robots. But nowadays, people have been trying to make robots which have bio-inspired designs. So as you can see here, the actuators, they run, they're located similar to our skeletal muscles. Okay, and so these actuators would they're special kinds of actuators, and they are placed exactly the way muscles are placed in our human body. Similarly for the hand again, this is one of the hand robot that we had made for a child in Almaty actually. So while we work with rehabilitation robots, we also work with assistive robots. So the difference is that there are certain neurological disorders which can be corrected, which can be cured, but there are a few disorders, neurological disorders especially, which cannot be cured. Even there are injuries, for instance, spinal cord injuries. Okay, if the spinal cord injuries cannot be cured, it's only the incomplete spinal cord injuries that can be cured to a certain extent. So something that cannot be cured, such patients would need assistive robots. So they would need some sort of gloves. So whenever they have to work, they will put on the gloves, and then the assistive devices can work, and then they can do their chores. And but yeah, so for assistive robots and rehabilitation robots, the criteria for design, actuation, control, everything remains the same. And as I said, that require a lot of bio-inspiration. The ones which we deal with, for instance, has such kind of spatial actuators. So we don't use electric motors in our robots. We rather use these actuators. We call them air muscles. So we inflate these. These are basically rubber tubes with some nylon shields cover. And so these rubber tubes, when they are inflated, they would contract and would expand when they are pulled up, when they are exhaled. So we use such kind of actuators which are quite close to our skeletal muscles. It is exactly the same as, I mean, when we plot their actuation, it comes out that their actuation is quite similar to our skeletal muscles. So talking about this bio-inspiration in wearable robots, as I was telling that it has to, bio-inspiration has to be considered for almost everything in right, since designing to using of these final use of these rehabilitation robots. Designing when we design the mechanism of the robot, we have to consider biological system, developing sensors, developing controller. Our human body has a controller which sits on our brain, actually. So if you look at a human body, it's nothing less than a robotic system. The musculoskeletal system or the bony structure can be taken as the mechanism. The actuators are muscles and tendons. Sensors, of course, sits on the skin, touch sensor, and of course we have many other sensors like eye. All five senses can take them as sensors to human body, and then the controller. Finally, the controller of this human robotic system sits on our brain. So we take all this into account, and then we design a rehabilitation robot. Now, what are different technologies that are involved in making a rehabilitation robot? By now, you might have understood that you would need, expertise from engineering, medicine, computer science. You need everything to create such kind of autonomous systems that we call robotic exoskeleton. Now, these robotic exoskeletons that we have can be actually classified in terms of their application, in terms of there's something called degrees of freedom. So I hope you understand, but let me reiterate. Degrees of freedom would mean that we use this word degrees of freedom for mainly for joints. So the joints, definitely the joints are made to move. Now, in how many directions the joint can move would decide on how many degrees of freedom a joint has. And when we have multiple joints, then there'll be multiple degrees of freedom. For instance, my shoulder joint can actually rotate in 3 directions, that is X, Y, and Z. If I simply consider my shoulder as a ball and socket joint, okay. So it can rotate about X, Y, and Z axis. So we got 3 rotational degrees of freedom at the shoulder joint. And if you talk about your elbow, roughly speaking, it can give you 1 revolute motion. So it has only 1 degree of freedom, which is rotational degree of freedom. Talking about your wrist, you can probably do all 3 again. So from shoulder to the wrist, the human arm has got 7 degrees of freedom. But when you consider the entire hand, then the number of degrees of freedom could be more than 40. So a robot is also classified based on how many degrees of freedom it is able to provide to us. In terms of actuators, there are different kinds of, there are certain robots, they use electric motors, others would use hydraulic piston cylinder arrangements, pneumatic actuators. The ones which we make use air muscles. And then the treatment aims also would, differentiate between rehabilitation robots. So there are CPMs, which are passive devices and used for motion training. There are devices which would be used only for range of motion trainings, and then further devices can be used for strengthening of joints. And so based on these, the classification is further larger, actually larger than what I've shown it here. But yeah, over the time when we will study the existing robots, we'll talk about these once again. So as I was telling you, based on the application, there could be upper limb exoskeletons and the lower limb exoskeletons. Upper limb exoskeletons, they require less force and torques compared to the lower limb exoskeletons, of course. But the upper limb robots, they require more complex motions because we do complex manipulation with hands, and legs are only used for walking different terrain. And so force and torque requirements are different for, and so the dexterity requirements are also different. So, I mean, depending on the application, the robotic exoskeletons have to be designed accordingly. If we have time, maybe Okay, tell me one thing. Are you able to hear this voice? You're not, right?
Can you play
No.
a little bit more?
No, we can't hear.
No.
You can't hear, right? Yeah. I had guessed that probably. Let me see if I can play this here.
Providing highly intensive physiological gait rehabilitation to severely impaired neurological patients is providing highly intensive physiological gait rehabilitation to severely impaired neurological patients is a huge challenge for health professionals today. This is where Hokoma's innovative solutions can help. The Lokomat is the world's leading robotic medical device that provides a highly repetitive physiological gait training, especially to severely impaired patients. The combination of adjustable orthoses, a patented dynamic body weight support system, and sensorimotor stimulation ensures the most physiological gait training on the market. Motivating real-time feedback results in active training participation by the patient and increased self-activation of residual functions. Therapists can continuously adapt training parameters to the patient's abilities at every stage of their recovery. The objective documentation of the patient's progress supports communication to the patient, medical experts, and health insurers. The safe training environment for the patient opens new possibilities to increase therapy intensity in efficient settings. Hokoma's Lokomat, the most trusted gait robot, getting your patients back on their feet.
Yeah, so did you see this? There's a lot of pelvic motion. And so the trunk was, going up and down quite a bit. We don't normally realize while walking how much we move vertically. And so, yeah, you have to consider everything while designing such kind of robots. That, if you don't provide this vertical motion, it would be really difficult for the person to walk with the robot as such. There's one more, I think. Okay, let me play this. This is how the Lokomat is being used. You need to lift the person using something called body weight support system. And maybe I can go a little farther. And the person is taken onto the treadmill. And okay, I don't need this thing. So after the person is made to stand on the treadmill, the robot mechanism has been brought in and has been fixed with the person. Now, this particular arrangement is necessary for the robot joint to remain in contact with the human joints. So before this, there'll be a lot of measurements to be carried out. Now, this particular joint that Lokomat has gives both rotational as well as the translational motion to the knee, as you can see. The ankle joint, unfortunately, is not actuated. We can see two springs there, both sides. And these springs are termed as foot lifter. So the springs will only help person lifting the foot off the ground during swing motion. So the person is in the air. Okay. For now, the person is on the air, in the air, and gradually he's being lowered down. And now he has touched the treadmill. This is again important to match the stride frequency with the speed of the conveyor belt on the treadmill. Which is again quite typical. Yeah. There's one more, I think. For children, now this particular robot helps them move and they can sit. Yeah. This is one which I have in my lab. I mean, I had basically 3 of such robotic devices. Maybe I can try and show you one of my. Wait. If we have time, I can quickly show you one from my own. Maybe I can share the screen now. So the one which we have, can you see this now?
Yes.
Yeah. So this was something that we took like in 2020 to one of the exhibitions. Yeah. Back to the presentation. Yeah. Full screen. There we are. So yeah, for vertical pelvic. Wait, yeah, here it is. Yeah. So this gives vertical motion here. So the entire robot would have many degrees of freedom, including some of these as active and others being passive. Another instance of a robot for the ankle joint was, again, I had many designs before. So this is my first design where you have a platform where person can place his foot. And these are the 4 actuators that would make it move all around, because the ankle joint has 3 rotational degrees of motion. And then it was slightly improved and then further improved like this. And now it's quite compact, and the actuators, they run in parallel to the shin bone, and quite user friendly. I mean, this kind of a robot can actually be used for the treatment of sprains that usually happen with the sports persons. It can be used for drop foot problem. Could be used for, I mean, for both injuries and disorders. You can use them. The one which we had last year, it was 2019 that we made this. It was used for, this is for the wrist, and this is for the elbow joint. For the wrist, we have one such kind of a robot, and there's another kind of robot. So there are 2 kinds of devices that we normally use for rehabilitation in total, in overall. Like, these are called end effector based or exoskeleton. So this is an example of exoskeleton, and this is an example of end effector based robot. So here what we do is, there's a platform where a user's hand has been clamped with some velcros or something, and there's a jockey kind of thing which you can hold on. Okay, and then the platform would move up and down. I mean, in all 3 rotational degrees of freedom, the platform move, and the wrist would move as well. The devices that we make are sometimes quite compact, but sometimes they're very big ones. Like, this is complicated though, but yeah, the shoulder joint has 3 rotation degrees of freedom. So we've got 3 motors here. These are very compact pancake kinds of motors with lightweight and high torque. So we call them torque motors. So these 3 would give the required shoulder motion. This is for the elbow, and this is for the wrist joint. It looks a bit complicated and intimidating, but in actual use it is not. We use it in our lab here. Yeah, but the shoulder one, it was made by one of my colleagues. He's recently become assistant professor in robotics department, IBIC. He did PhD under me, and so this mechanism was used for the shoulder rehabilitation. So the idea was to not have motors on the joint, because the motors, they are very heavy. So we kept these motors outside somewhere else, and using the cables, the motor rotation or actuation was transferred to the shoulder joint here. Yeah, I think this is all for today. We should better stop now. So yeah, today I was only trying to have some sort of a chit chat with everyone and give you a kind of overview of what we are doing here and what this course is about. And did you have time to go through these 2 videos that I had shared on Moodle? Actually, I think it was very short time. So yeah, please see if you get time to look at these 2 videos. So one of them is from Hugh Herr, as I was telling, the professor at MIT, Massachusetts, and it's a big inspiration for everyone. and the other one is from a professor who's in Stanford. So they are working on rehabilitation robots, and they are one of the pioneers, good research, and our competitors. So for the next session, we'll try to understand the kinematics and dynamics of a human system. Apart from that, I'll try to introduce you to one of the existing softwares on biomechanics, where we'll try to quantify human motion trajectories, joint torques, properties of various musculoskeletal elements. So, I mean, such softwares are sometimes necessary to understand the human system that these robots trying to manipulate. And as I was telling you, that while controlling human system, we need to learn, we need to model these human systems as well. So these kind of softwares are necessary. But when we work with our systems, we create these the model of human system. We try to create with less expensive algorithms. So we have our own higher level algorithms, because otherwise what you need to do is you need to model the entire musculoskeletal. Okay, if you're trying to model it, you have to model the bones, then model ligaments, then muscles and tendons. So there'll be one equation for everything. Okay, and then put all these equations into one matrix, and then create a dynamics equation, and then couple this dynamic equation with the robot's dynamic equation. So it becomes very complicated. So we will not go into all the details. Just to share with you that how this, why do we need to know human body? Because we have to design a controller, and to design a controller, we have to obtain a mathematical equation for all these elements and all these parts of human musculoskeletal system that we are trying to move on. So yeah, you don't have to go through those things, the details of controller or something like that, or modeling maybe. But there are certain, I mean, why we trying to learn software, for instance, is to see if we can use these softwares to evaluate when a person is improving. Okay, so while we're trying to use these devices with the patients, we work with them, and every time we try to evaluate from the sensor values that we get. So, I mean, given with simple anthropometric measurements of a person, you are able to predict some of the things, but for further details on how the person is improving and how his functions are, you probably need such kind of software to learn. So yeah, I wish you all the best. Wish you best of learning, and let's see how it goes. Bit nervous though, because we have students who are already doctors, and if I start talking about anatomy or such kind of things, probably you know more than me. But I can tell you what I know, and maybe you can also share with your experience what you can. I mean, let's work together. Let's study together. So thank you for being with us, and if you have questions, we can further continue.
Just want to say thank you so much. It's very, very interesting, the lecture today.
Thank you, Mashid. I really appreciate getting up early in the morning and joining us. So
of course,
yeah, you're most welcome here. You will find it's very cold over here, and there's snow everywhere. But the good thing is that in Kazakhstan they manage cold very well. And if you go to some other country, like last time I had been to UK during the time when it was snowing over there, it was really difficult to even drive on the streets. But here everything is managed quite well. Yeah.
That's right. Yes.
Mhm. So if there are no more comments or questions, we can close the session for today and enjoy the rest of your day. And I'll see you once again next Tuesday.
Thank you.
All right.
See you.
Thank you. Bye.
Bye.